The good side of alternating series comes from something that is called the alternating series test. Not very imaginative, but it works. And this test works like this. It says that an alternating series for which the sequence of positive terms decreases to zero will in fact converge. Okay, so it's a very easy statement, very easy to check. Now remember, by the way, that what I'm talking about here are not the terms of the series, they are the terms of the positive sequence from which we construct the alternating series. So what happens is that if that sequence is actually decreasing and it decreases to zero, that's enough for us to conclude that the series is convergent. Now notice that this looks like the converse of the divergence test. Remember, divergence test tells for any series, if the sequence does not go to zero, the series is divergent. This gives us a partial way back. First of all, it only applies to alternating series, and then it requires the absolute values basically of those terms, so just the positive part, to decrease to zero. Why would that work? Why is that true? Well, again, I'm not going to give you a formal proof, but hopefully enough of an argument to convince you that it does. Okay, so let's say that we have this series and we start at negative a1. Okay, so let's say that our series is the form negative 1 to the n, a(n). Okay, so we start at negative a1. And then what we're going to do is, to get the next partial sum, we have to add a2. Well, that will take us a little bit further beyond. Now the next term, we're going to be subtracting it, right? Because next one is going to be minus a3. But remember, the sequence we're assuming is decreasing. Therefore, we're going to go back, but we're not going to go all the way to negative a1. We're going to stop to negative a1 plus a2 minus a3, which is going to be a little bit closer to where we were before than the original minus a1. And then I can repeat the same argument. By adding a4, I'm not going to go back or even beyond the previous term, the previous partial sum. I'm going to fall short of it. Okay? And then if I keep using this same argument, every time I'm adding something, I'm adding and subtracting alternatively something which is getting smaller and smaller and smaller. So my partial sums are going to be narrowed for more and more and more and more towards some point which will turn out to be the limit. So it's a very simple test. It works quite nicely, and it guarantees convergence. Of course, it does not tell us what the series will converge to, but it does something pretty close to it, because by using the same argument, you can see that the partial sums of the series can be used as approximations. Notice that as we were adding and subtracting those terms successively, the partial sums were bouncing above and below the limit L, and every time they were bouncing by a lesser and lesser amount, and therefore the nth partial sum is going to be no further away from the limit than the next term. So the difference between the nth partial sum, Sn, and the limit we're looking for, which is L, is no more than a sub n plus 1. So the next term tells us how far away we are from the real limit. And this gives us, of course, a way of approximating the value of this series. Alright, so what we have seen is that series whose terms are eventually positive or eventually negative, if they converge, then they converge in a very stable way. We can rearrange the terms as we want. These alternating series, or more generally series with infinitely many positive and negative terms, are a little bit more unstable. And therefore, we may want to, actually turns out to be a useful thing, to differentiate what kind of convergence we have. Is it a convergence for which we don't have to worry about the order of rearrangement, or is it a sequence for which, or a series and a convergence for which some problem may pop up? So what we're going to say is that a series is absolutely convergent if the series consisting of its absolute values is convergent. Of course, the series consists of absolute values is a positive series, is certainly eventually positive, but in fact always positive. So if that one is convergent, everything is nice and dandy. And in fact, in this case, and again, I'm not going to go through the proof of that, but it's the same basic ideas for proving this fact, that if a series is absolutely convergent, then it is converged, convergent? Well, the idea is, well, if by adding up all the absolute values, I'm just getting to a finite value. By adding some of those terms and subtracting some more, I cannot get much farther away. In fact, I have to get to some kind of closer, smaller number rather than the sum of all the absolute values. Not only this, but in fact, any rearrangement will converge to the same value. So if a series is absolutely convergent, no problem with the commutativity. We can rearrange the terms of the series and they will all converge to the same thing. However, if a series is convergent but not absolutely convergent, then we say that it is conditionally convergent, okay? Meaning that it's convergent as long as we keep the pluses and the minuses, but if we drop them, then we have a problem. These are the series that create the difficulty. So the terms of a conditional convergence series can be rearranged to converge to any number or to diverge. So this is the situation where we're going to have problems with. So even with alternating series, some alternating series are absolutely convergent. In that case, no problem. We can rearrange the terms as much as we want and we'll always converge to the same thing. But some alternating series are conditionally convergent. In that case, well, their convergence is finicky. Change the order and you may end up with something different. May, not necessarily, but you may end up with something different.